Okay, so in this lecture, we're going to talk about the LU decomposition and how we can use it to do efficient computational linear algebra. So we've already seen that if we have a matrix A and a right-hand side vector B, we can solve for X with Gaussian elimination followed by back substitution. And that requires on the order of 1/3 n cubed operations, where n, little n, is the number of rows in A. Well, if we had a decomposition of A into two matrices, L and U, where L is lower triangular that means it has a structure where it only has entries on the diagonal and below, and everything above the diagonal is 0. So there's an example in the 3x3 case. And in this decomposition, U is upper triangular. Likewise, for an upper triangular matrix, you're going to have entries only on the diagonal and above it, and everything below it would be 0. Again, an example for the 3x3 case, but these hold for higher dimensions as well. So if we have this kind of decomposition, so again, A equals LU, we can plug LU into our equation. So then we'll have LU, the vector of unknowns X, the right-hand side vector B. And what we can do is then divide this into a two-step procedure. So what we're going to call U times X, we'll call Y. Okay, so then this equation will be Ly equal to B, right? L is lower triangular, and so if we have this systems of equations, we can use forward substitution. We'll talk about what that looks like in a second. We've already seen back substitution from Gaussian elimination, but we can use forward substitution, and that only requires on the order of n squared operations. Okay, and so we'll solve this for Y. So once we know Y, we then have a new system of equations that is Ux equal to Y. And we can solve this. Again, U is upper triangular, so then we can use backward substitution. And again, that takes on the order of n squared operations. And so what we then have is the total solution, once we have the LU decomposition, is on the order of 2n squared, which of course is less than solving for Gaussian elimination. Now, you do have to perform the LU decomposition. So I'm going to say performing the LU is the same as Gaussian elimination, so it's on the order of 1/3 n to the cubed. However, you only have to do this once, and then you could solve for multiple right-hand side vectors B. So it turns out that we already have a procedure for putting a matrix in upper triangular form, and that's the row operations of Gaussian elimination. So we know that we can take A into an upper triangular matrix U by performing row operations. And namely, those row operations are the type where you take a row I and then it gets replaced with itself minus some factor times row J. And so if we were going to undo this row operation, the undoing of that row operation would be Ri plus Mij, Rj, right? So if you performed this operation and then followed it with that operation, you'd get back the same matrix A, right? So what we're going to do is we're going to transform A into U by doing the first type of row operations, and then we're going to start with an identity matrix, and we're going to perform the second type of row operation. So I'll call this 1. We'll do the type 1 to take A from U, and we'll do type 2 to take the identity matrix into L. And so this is how we can do an LU decomposition. So let's look at an example. So here I have a matrix A. I've written out the row operations that takes it to U. So over here we have a matrix U. And then what we're going to do is we're going to do the opposite of those row operations on the identity matrix. Again, or the undoing of those row operations. So if you notice, this guy is undone here. This guy is undone here, and this guy is undone there. Now, so then you have an L and U matrix. Now, it turns out that what you see is that these entries in the L matrix are simply the factors in the operation. And so you don't actually have to perform the row operations through this observation. You can just place those multiplication factors into the location in the L matrix directly. And that simplifies the task at hand somewhat. So just checking our results with Python, we write out the matrices that we solve for L and U in terms of NumPy arrays, and then we'll use the multiplication symbol. So the @ symbol in Python is the multiplication symbol for matrices. And you see that we do, in fact, get back identically the original matrix A. So here's just an implementation for the pseudocode for such a thing. Again, it's very similar to just putting the matrix in row echelon form. It's just now we're going to initialize U equal to A, and then basically perform the row echelon Gaussian elimination operations on U. Meanwhile, we've initially set L to the identity matrix, and when we compute the factors in producing the row echelon form of U, we just go ahead and place them into the L matrix. So it's a fairly simple modification of the normal kind of row echelon form of the matrix that you use in Gaussian elimination. Now, let's return to this for 1 second and just notice that because of this step right here, that's the diagonal entry of the division by the diagonal entry of U, even a single zero, right? Even a single zero on the diagonal of U, which, because U is initialized from A, would mean a single entry on the diagonal, 0 on the diagonal of A, would cause this algorithm to fail because you're going to get a divide by 0 error, okay? So we can make the algorithm more robust by simply keeping track or performing permutations of rows of the matrix such that there's never a diagonal entry of 0. And what we can do then, again, if we have an initial system of equations, AX equal to B, that we're replacing with LU equal to B, then all we need to do is keep track of the permutations in a matrix P, and we're going to multiply both sides of the equation by P in order to do that. So then just notice that if you do the two-step forward and back substitution, you have to multiply P by the right-hand side vector B in order to do that if you're going to use this PLU decomposition. So let's go ahead and take a look at what the pseudocode for the PLU decomposition is. And it's nearly identical to the one before, except for, again, Now we're going to test if there is a 0 on the diagonal, then we'll just swap rows here and keep track of that by having an initial permutation matrix that's equal to the identity matrix. And we just, whenever we swap a row of U, we also swap a row of P. And so that's, P will just be the permutations of the identity matrix. So again, we've already discussed how we're going to solve these equations. So the first step is the forward substitution process. We've already looked at backward substitution when we looked at Gaussian elimination. In a backward substitution, you start at the last row and eliminate up the rows. Well, here in forward substitution, because you have a lower triangular matrix, you're going to start at the first row and eliminate down the rows. And so this is the pseudocode for that. And then follow that with the pseudocode for backward substitution, which is identical to that from Gaussian elimination. And again, just remember, I'm going to write it down one more time. You know, in the forward solution step, we're solving this equation. However, if we have a PLU decomposition, we have to multiply the right-hand side vector by b before we solve for y. And then everything proceeds as follows from that. And then we can perform the backward substitution like so. Now let's take another look at LU decomposition. And if we have our L and U just generically, and right now we're only writing this down for a 3x3 matrix, but the ideas apply for larger dimensions. If we were to go ahead and multiply out the components of L and U to get a matrix like this, well, we could see by inspection, if we use the algorithm where L has ones on the diagonal, like we did before, assume that we have ones on the diagonal, like we did before, then we can see by inspection, we can just write down the fact that U11 will equal A11, U12 will equal A12, and this should be 13, 13 equals to A13. And again, this is because we have ones on the diagonal. Likewise, these terms will be 1. Once we have that, we can see we have enough information then to go ahead and solve for the rest of the first column, namely L21 is equal to A21 over U11. U11 is known, it's A11, of course. The last thing we need to figure is the third entry on the first column here. Again, that is A31 is equal to L31 is equal to A31 over U11, again, which is known. Now we have enough information to solve for the rest of the second column, namely U22 is equal to A21 minus L21 U12, all of those are known, divided by L22, which is simply 1, right? And we could continue this operation for the rest of it to eliminate all the rest of the terms. And the algorithmic design of this is called Doolittle's algorithm. And similarly, there's one called Kraut's, which instead of using ones on the lower triangular matrix, uses ones on the upper triangular matrix. Both of them have the same number of operations, so neither is more efficient than the other. It's just a matter of preference. By the way, I don't think I mentioned it, but LU decompositions are not unique. There's an infinite number of matrices L and U that can multiply and become A. So here's the pseudocode for the Doolittle algorithm. It's fairly similar in many respects. For at least once you've done this step 4 here, the last operation is identical to the row operations in Gaussian elimination. Here's the pseudocode for the crowd algorithm. Again, it's just very similar to the Doolittle algorithm. I'm not going to go into the details there. And then finally, we have another algorithm that we'll call Cholesky decomposition, which just uses a special LU decomposition. So and this only works if A is symmetric. A matrix is symmetric if it has the same entries above and below the diagonal. So for like a 3x3 case, if you had something like this, that would be a symmetric matrix. I only wrote the negatives here for the next thing, and that is that it has to be positive definite. And a matrix of this form that has positives on the diagonal is symmetric with negatives on the off diagonal will be PD, positive definite, and that's why I wrote this that way. But the true definition of positive definite is if all the eigenvalues of the matrix are positive. And if you haven't had a linear algebra course, don't know what eigenvalues are, we'll cover those in the future. But if you have a matrix that's positive definite, then you can have an LU decomposition where U is equal to L transpose. And with that, then you can write this like L transpose. And so then you only need one matrix L, and this is the algorithm to come up with that decomposition. And that is called the Cholesky decomposition. Again, once you have this Cholesky decomposition, you can use the forward and back substitution for solving systems of equations the same way you would with a regular LU decomposition. We can use these ideas to solve for the inverse of a matrix, and basically the way we're going to do that is we're going to set our right-hand side vectors, our right-hand side vector to be a collection of right-hand side vectors that are identically the identity matrix. And we're going to solve the system of equations basically for B1 as the solution vector, the right-hand side vector, followed by B2 as the right-hand side vector, followed by B3 on up to Bn. And basically what we're doing is we're solving for the inverse of A one column at a time through this procedure. And so there's the pseudocode for that. Basically, we'll just do the LU decomposition and then repeatedly solve one column at a time, do the forward and back substitution to get the inverse. Finally, we can also use the LU decomposition to solve for the determinant of a matrix. So from kind of rules of linear algebra, if we have a matrix A that is equal to 2 matrix L times U, then the determinant of A is equal to the determinant of L times U, the determinant of U. Well, additionally, we have a rule that says that for an upper or lower triangular matrix, the determinant is equal to the product of the entries on the diagonal, right? So just to write it out, if we have, so L is equal to, again, I'm just going to write the 3x3 case, but it applies for higher dimensions. So any matrix that has this type of form, then the determinant, again, of L is just going to be the product of the diagonals. And the same holds for an upper triangular matrix U. So once we have that, we can, if we use, say, Doolittle's algorithm, where we know we're going to have 1s on the diagonal of L, well, the product of the diagonals would just be 1, and therefore all we need to solve for the determinant of A is the determinant of U, and again, it is just the product of the diagonals. So the determinant of A if we use a lower triangular matrix with ones on the diagonal, is simply the product of the diagonal of U. And so that's a very easy, straightforward way to solve for the determinant of a matrix. If we have a PLU decomposition, then again, where L's are the ones on the diagonal of L are there, then it reduces to the determinant of P, which may cause you to think that we need to also solve for the determinant of P somehow. But if you recall, P is just a permuted identity matrix. And so let's see what happens if we take the identity matrix and just make a couple of random permutations to it and look and compute the determinant. For this, we'll use the built-in NumPy linalge determinant function. And so what we're going to do is swap the first two rows and print the determinant, swap the second and third row, print the determinant, swap the first and fourth row and print the determinant. So here we're just kind of doing pseudo-random permutations and printing the determinant. And what you'll see, what happens is we always get 1 and it just alternates sign. And so we can actually summarize this. This will always be true for a permutation matrix. And we can summarize that like this. The determinant of P is going to be 1 for even number of permutations or -1 for odd number of permutations. So what that means is that in order to compute this, all we have to do is we don't have to actually store P, but rather just store the number of permutations of P and then set this equal to either positive or -1 based on the number of permutations of P. Then compute the determinant of U via the diagonals of U. And so that's how we can use the LU or the PLU decomposition to find the determinant of a matrix.